All right, guys. So in this video, we are going to talk about the ideal gas law. All right. So this gas law is slightly different because it's only got, as compared to the combined gas law, there is only one set of variables. So nothing is changing in this one. All right, so we are either trying to find volume, pressure, or temperature of a given amount of mass under stated conditions. So nothing is changing. And our equation is PV is equal to nRT. So you guys should know that P stands for pressure, V stands for volume, and T is temperature, which still, as always, must be in Kelvin. One thing I do want to add, though, is that your volume in this one must be in liters. All right, so in the last one, it didn't really matter as long as you had the same volume, but this one it does. All right, so temperature must be in Kelvin, volume must be in liters. Okay, guys, and then we have some new variables. So the first one is N, and it stands for number of moles. Yay, moles are back. I don't know, you guys probably already saw moles, but anyways, moles. Yay. And it just says you can substitute moles divided by molar mass for this, essentially, which is basically just doing the conversion in the problem instead of doing it after the problem. Then our other new variable that you guys probably haven't seen before is, of course, that R value. And R is the universal gas constant. Okay, so it's a constant. It's on the formula chart, but I'm going to go through it with you guys real quick. So R can have several different values. So it can either be 0.0821 liters times atmospheres per mole, divided by moles times Kelvin. 62.4 liters times millimeters of mercury divided by moles times Kelvin, or 8.314 liters times kilopascals divided by moles times Kelvin. So guys, we have these three different R values, all right? And basically we have to choose which R value we use based on the one thing that's different in their units, and that's the pressures. So like in our first one, it's liters times atmospheres. So if we're in atmospheres, that's the R value we would use. Next one is liters times millimeters of mercury. So if we're in millimeters of mercury or torque, so on the same scale, that's the one we would use. And then finally, our last one is for kilopascals. So those are going to be the three R values. And I always say it's kind of like ice cream. You have to match your ice cream to your topping. So we have to match our R value to our pressure value. They have to go together. All right. So this equation's pretty easy because it's only one set of variables. So when we go through our problems, we're going to label the different variables in our problems and then plug it in and solve it. All right. So our first problem says how many moles of oxygen must be put in a 500 milliliter flask at 20 degrees Celsius to have the pressure of the flask of 1.77 atmospheres. Okay, so let's go ahead and label all of our variables and figure out what we are looking for. So the first thing it says is how many moles of oxygen. So that would be N. All right, and that's our unknown. So N is like a question mark or X, whatever you want to say. Must be put in a 500 milliliter flask. That's our volume because we're in milliliters. Now, guys, remember I said it has to be in liters. So you can do your real quick conversion. So King Henry died by drinking chocolate milk. All right, we're in milliliters. Want to be in liters. 1, 2, 3 to the left. So 1, 2, 3. So it would be 0.500 liters. At 20 degrees Celsius, there's our temperature. But again, we must be in Kelvin. So we'll add 273 to that, which gives us 293 Kelvin. And then finally, last value that we see is 1.77 atmospheres, which is our pressure. So you guys can see we have P, V, N, and T. The only one we're missing is R. It's a constant, so we have to plug it in from our equation. Since my pressure is in atmospheres, my R value that I'm going to use is 0.0821. Okay? So now I'm going to go ahead and take my equation. So PV equals N RT. I'm solving for n, so I'm going to manipulate my equation so that n is all by itself. All right, so in that case, that means I'm going to divide both sides by RT. So we get that n is equal to PV divided by, oops, if I can write, RT. All right, and we'll just plug it in. So my pressure is 1.77 atmospheres times my volume is 0.500 divided by my R value, which is 0.0821 divided times my temperature, which is 293. Now, guys, you're going to plug this into your calculator. I do want to caution you guys that when you plug it in, to make sure that you put the bottom all the way in parentheses, or else you'll end up with some bad math. A lot of you guys have also reached out and been like, how do we do sig figs for like gas laws? And guys, it's really easy. It's just the fewest number of sig figs overall. So like my first number has 3. Second number has 3. This one's a constant, so we wouldn't count that. That one has 3, so my fewest number is 3. So my answer should have 3 sig figs. So that would give us 0.0368. And then don't forget your units, which is moles. Boom. That's it. That's the ideal gas law. Not so bad. Okay. Let's do another one. All right. And if you guys noticed, when I went through, I kind of went ahead and the first time I read through it, I underlined all the variables or highlighted all the variables and then went back and labeled them. So I would highly encourage you guys to do that as well. All right. So first things first is it says if 1.17 grams of helium are put into a 5-liter container at 10 degrees Celsius, what would be the pressure in the container? And then it does tell us in torr. All right. So first things first is I have that 1.77 grams of helium. So it's in grams, but I can convert it to moles. So that's going to be my N value, and I'm going to convert using my molar mass because I know it's helium. So I'm going to convert using my molar mass to a 5-liter container. That's volume at 10 degrees Celsius. So again, it's temperature, but we need to add 273. So that gives us 283 Kelvin. And then what would be the pressure? So we want to know pressure. And again, we want to know in torr. All right. So the only variable that's not in our problem, once again, is the R. All right, guys. And so we need to figure out which R value to use. Like I said, millimeters of mercury and torr are on like the same scale. So we would use the same R value for them. So we're going to use 62.4 as our R value here. All right. So first things first, I am going to convert my grams to moles. So if I have 1.17 grams of helium, using my molar mass from the periodic table, 4 grams of helium is 1 mole of helium. Plug that into your calculator and I get 0.293 moles. Just for the sake of space, I'm going to manipulate my equation just in my head. So sorry, guys. But we have PV equals nRT. I want pressure all by itself, so I'm going to divide both sides by volume. So I end up with P is equal to number of moles times our ideal gas constant times temperature divided by volume. We'll just plug everything in. So my number of moles is 0.293 times my ideal gas constant, which is going to be 62.4, times my temperature, which is 283, all divided by my volume, which is 5. Plug it into your calculator. Once again, our fewest number of sig figs is 3, so my answer should have 3. And I got 1,030 torr for my answer there. All right. Last one for this ideal gas law. Excuse me. Last one for this kind of version of the ideal gas law. And then we're actually going to talk about another version of the gas law, ideal gas law as well. All right. So it says, what is the molecular mass of a gas if 20.6 grams of it in a 500 milliliter container exert a pressure of 2,500 millimeters of mercury at 350 Kelvin? Okay, so first off, our problem is asking for molecular mass. All right, I'm going to tell you guys this problem is a little bit different than what we've been doing. It's the same idea, but real quickly, I just want to go ahead and kind of give you guys a definition of molecular mass. So molecular mass, is equal to the mass divided by however many moles, right? The molar mass is the mass of 1 mole. So if I wanted to figure out basically the molecular mass of a substance, I could say, well, what's the mass of that substance and then how many moles are in that mass? And I can get the molecular mass that way. So we are going to use this eventually, that 20.6 grams, but we're actually going to wait till the end. So what I'm going to end up doing is I have right here 500 milliliters, that's volume. So again, need to convert it to liters. So move our dot 3 times to the left, end up with 0.500 liters. Then we have pressure and we have temperature. So guys, we can solve for number of moles here. So we can solve, we don't know what N is. We can solve for number of moles and then use the mass and the moles to figure out the molar mass. Okay, so the only thing we're missing here is our R value. We have millimeters of mercury, so we're going to use our R value that has millimeters of mercury in it. So that is going to be 62.4. All right, so then once again for space, I'm just going to manipulate my equation. So N is equal to PV divided by RT. And then we're going to plug everything in. So 2,500 times 0.500 divided by my R value, 62.4, times my temperature, which is 350. Okay. Should have 2 sig figs in our answer there because 2,500 only has 2 sig figs. So I got 0.057 moles. All right. And so then I can plug that into my mass divided by moles equation. So I have my mass is 20.6 grams divided by my moles, which is 0.57 moles. And I got 360 grams per mole as my molar mass. I got 361, but since this only has 2 sig figs, I would say that only has 2 sig figs, so I got 360 grams per mole. Okay, that is the first kind of ideal gas law. So we have some deviations of it, basically some ways that we can manipulate the ideal gas law to solve for other things as well. So we can actually manipulate our equation to solve for density. So we can use this equation, PV M equals MRT, where basically we've just subbed in, instead of having a number of moles, we've subbed in our mass and our molar mass. And when we actually simplify that out and kind of think through like the different like variables we have there, we can actually get that PM is equal to DRT. And how I normally write this one is that my molar mass is equal to DRT over P. And I call this the CAT equation. Most people call this the CAT equation. All right, so molar mass is equal to dirt over P. So if you don't have a cat, cats bury their pee. which is a fun fact for you. So molar mass is equal to dirt over P. So it's just like a way to remember this deviation. Normally, this is something that you would have to memorize, is memorizing that basically molar mass is equal to dirt over P. So the only point of like this one really is to, that's kind of how we derive the second equation. So this is like the important one. So, again, we get it because if you like divide both sides by volume, you'd have mass over volume, which is density. So it plugs in there. So if you wanted to find the density, this is the equation you would use. Okay, so let's do it. So this first one says, what would be the density of oxygen gas at 70 degrees Celsius and 3 atmospheres of pressure? Okay, so what do we have? We want to find density. So density is equal to our unknown at 270 degrees Celsius. So it's temperature, but we need to add 273 to it because we want to, it needs to be in Kelvin. So when we add 273 to that, we end up with 343 Kelvin. 3 atmospheres of pressure is our P. So we're missing kind of 2 variables, our R value, which again, we just match to our pressure. So in that case, it's going to be 0.0821. Since our pressure is in atmospheres, we pick our R value that has the units of atmospheres in it as well. Then the other thing we're missing is our molar mass. But we know it's oxygen gas, so we can easily solve for our molar mass. So oxygen gas is O2. So its molar mass would be 32.00 grams per mole. All right. And we got the 32 because there are 2 oxygens. Okay, so then it's just solving for basically solving your equation. So density is equal to if I could manipulate the equation correctly, that'd be great. Density is equal to pressure times our molar mass divided by RT. All right, so pressure is 3 times our molar mass, which is 32, divided by our R value, 0.0821, times our temperature, which is 343. So then plug it all into your equation. Our answer should have 2 sig figs because our pressure only has 2 sig figs. So it's our fewest number. So we end up with 3.4 grams per liter as our density. There you go. All right, one more. If the density of 3 more technically. Sorry, guys. One more on this page. All right, if the density of a gas is known to be, 1.96 grams per liter at 755 torr at 5 degrees Celsius, what is the molecular mass of this gas? All right, so we have our density, we have our pressure, we have our temperature. We need to add 273 to that. So that gives us 278. And we want to know the molecular mass. So that's our unknown. All right. The only thing we're missing is our R value. Again, our R value needs to match our pressure. So since we're in torr here, our R value is 62.4. Okay, so molecular mass is equal to dirt over P. So then we just plug everything in. So 1.96 times 62.4 times 278, all divided by our pressure, which is 755. Okay, our fewest number of sig figs here is 3. So I got from my molar mass 45.0 grams per mole. Okay, guys, 2 more problems. These are a little trickier, both of these next 2 problems. They're not super hard, but they're just a little trickier. So let's go ahead and get started. So this first one says, if the density of a gas is 1.53 grams per liter at 750 torr and 20 degrees Celsius, what is the density of the same gas at 1.5 atmospheres and 7 degrees Celsius? Okay, so we actually do have two sets of variables here. So in our first set of variables, and I'm going to kind of label them density 1, we have the first density, we have our first pressure, and we have our first temperature. Again, we have to add 273 to that, so we end up with 293. Okay, and we want to know what the density of the same gas is at a different pressure and a different temperature. Okay, so what I'm going to do is I'm going to look at, so what am I missing? So I have the density of this first one, I have the pressure, I have the temperature. What I don't have is the molar mass. All right, so we know the molar mass should be the same for both of these situations. So what I'm going to do is I'm going to solve for the molar mass of the first gas, and then I'm going to use that molar mass and plug it into the second gas to solve for my density. Okay? So for my first gas, my molar mass is equal to dirt over P. So my density is 1.53. My R value, since I'm using torr, I need to use the R value that matches with torr. So that would be 62.4 times my temperature, which is 293, all divided by my pressure, which is 750 torr. 2 sig figs. My answer should have 2 sig figs because my pressure only has 2 sig figs. So I end up getting that my molar mass is 37 grams per mole. Let me fix my 37 so it's easier to read. All right, so now I'm going to take my molar mass because it should be the same, plug it into my second set of variables, and this time solve for density. So density is equal to pressure times our molar mass divided by our R value times temperature. So my pressure is 1.5 atmospheres times my molar mass, which is 37 grams per mole, divided by my R value. This time I'm in atmospheres, so I need to use the R value for atmospheres. So that would be 0.0821 times my temperature, which is 280. So plug all of those in to your calculator. Your answer should have 2 sig figs. So we end up with 2.4 grams per liter. So my density would change and my density would become 2.4 grams per liter. All right, last one. So this one says, what is the molar mass of a substance that weighs 0.46 grams at negative 14 degrees Celsius in 33 psi in a tire that contains 2.25 liters? Okay, so I want to know what my molar mass is, so that's my unknown. All right, I have my mass, I have my temperature, I need to add 273 to it, so that ends up as 259 Kelvin. I have a pressure, it's in PSI, so I already kind of know I'm going to need to convert that because I don't have an R value for PSI. So we'll come back and convert that. And then I have a volume. Okay, so I want to solve for molar mass. So I really kind of want to use the molar mass is equal to dirt over P equation, but I don't have my density. However, I can solve for it because I have my mass and I have my volume, and I know that density is equal to mass divided by volume, so I can plug that in. 0.46 grams divided by 2.5 liters. And I got that my density is 0.18 grams per liter. Okay, and then like I said already, since we are using the R value here, we don't have an R value for PSI, so we do need to convert PSI as well. So 33 PSI, 14.7 PSI. This is all from, it's on your formula chart. I don't know if PSI is. I don't think PSI is. But it's the conversions for pressure on your formula chart. So 14.7 PSI is 1 atmosphere. So 33 divided by 14.7 gives us that this is 2.2 atmospheres. Okay, so then we can plug it all into our equation. So molar mass is equal to 0.18 of our density. Since I converted to atmospheres, 0.821. Temperature is going to be 259 all over our pressure, which is 2.2. Okay, and so then we will plug that in to our calculator. Our answer should have 2 sig figs because our smallest number has 2 sig figs. So I got that our molar mass would be 1.7 grams per mole for our molar mass. That's it. That's ideal gas law. Hopefully this video was helpful. I know doing like a whole bunch of math problems is kind of boring. So I apologize, guys, for the boringness of this video, but you're almost done. You should only have 1 more video notes to watch for the year, and then you're done with chemistry. Yay! Okay, bye.